Hey, welcome to Ones and Zeros. My name's Ben, and today we are doing another of our STM32 Basic series videos. In this one, it's kind of going to be following on from the STM32 bus architecture video that we did recently. This one, however, is going to be taking a bit of a look at clocks with STM32 devices and the clock side of the reset and clock control system in those devices. We will be doing a bit of stuff, just as some examples, with our STM32 F411 Nucleo 64 board. This guy right here, that we've used in a lot of videos for this series, but much like the bus architecture video, we're also going to be taking a bit of a look at some of the differences between different members of the STM32 family as well. Just so you can get a bit of a feel for, some of the similarities, some of the differences, and from there, hopefully get a bit of a better idea of an approach to dealing with clocks and setting them up, different features that you may find in different devices, things like that. So let's get stuck into it. If we jump to this one, might get me out of the way for the moment. We can see this is the Quartz Arc code base for the F411 Nucleo board that is available on GitHub, and we've just got the clock configuration section of the CubeMX configurator tool set up. So although I don't use the configurator tool to actually generate code because I don't like the code it generates, there is a couple of things like the clock configuration screen that do come in really handy for figuring out different things related to the clocks and configuration and stuff like that, as well as giving us a good view of some of the things that we need to be aware of when dealing with the clocks. So some of the things that we'll notice are common across most of the STM32 devices is that there is a couple of clock sources internal to the STM32 devices. Typically, there is some differences there, but you'll normally find that there's going to be an LSI or low-speed internal clock and a HSI or high-speed internal clock. Typically, your low-speed internal clock is going to be a 32 kilohertz signal that is used for one of the clock sources to the real-time clock. So we can see the real-time clock multiplexer there where we can actually select between that or a couple of other options. And our high-speed internal clock is a clock source that we can use to be able to provide a clock signal to the rest of the system. Now, those two clock sources are typically not going to be 100% accurate, and you may find that two devices, say if you had two F411 devices side by side, they may produce slightly different frequencies with their internal clocks. And in this case, we can see that this is saying that it's a 16 megahertz clock. You'll possibly find that it's not going to be exactly 16 megahertz, and you might also find that depending on the temperature of the chip and various other factors that you might get some drift there with the frequency. It's typically not too bad and usable in most cases, but it's good to be aware of that. This is part of the reason why we have the option to be able to provide additional clocks from outside the chip. So we can also see we have an LSE input or low speed external input and a HSE input or a high speed external input. Again, the low speed one primarily being used for the real-time clock and is typically going to be a 32.768 kilohertz crystal, whereas our high-speed external is normally a crystal or another clock source that, again, we're using to help derive the clocks for all of the other parts of the system. So in the case of this particular board, there's a crystal that has been connected up to the chip that is being used for ST-Link programming and for the debugger, and that is then using one of its clock outputs to provide the 8 megahertz clock to the F411 chip. So it's actually getting its clock from another STM32 device, which is something that you can do, or you can hook a crystal directly up to the particular device, as you may see on certain other devices that you may work with. So there is some options there. Typically, you're going to have the option to be able to select for the rest of the system between a few different clock sources. And we can see here we have the ability to select between the high-speed internal, high-speed external, or the PLL clock. And in most cases, with most projects that I develop, I'm going to be using the PLL clock. The PLL itself is basically a tool that we can use in order to be able to take an input clock and turn it into a different frequency. And typically in the case of an STM32 device, you're going to be stepping that frequency up to a higher frequency so that you can then use that to run the system at a frequency that is higher than what the crystal or the external clock source is actually providing. The PLL can take its clock source from typically high-speed internal or high-speed external clocks. In this case, we can see that it's currently showing as being configured for the high-speed internal clock. And then there's various settings that we use for the PLL. So we have a divider, a multiplier, and another divider to be able to derive a specific frequency. And we'll have a look at that in a moment. We'll see here that from our system clock multiplexer, it gives us a bit of an indication of what the system clock speed is. And we then have the option to be able to add a prescaler if we would like to drop that clock down to a lower speed. And then that splits out to our various other clocks in the system. So this is where, if you've seen the bus architecture video that we did, some of this stuff might make a little bit more sense. So we've got various clocks being split off from here. So we've got our F clock, which is actually our CPU clock here. We've got the clock going off to our system timer, or our SysTick timer, which we use in the Quartz Arc code to be able to help do things like task scheduling. We've also got the clock going off to our AHB bus, or Advanced High Performance bus, which, if you've seen the bus architecture video, is the main bus that connects the CPU and the high-speed peripherals to the peripheral buses. We've also got the peripheral bus clocks as well, and then we've got the clocks that are going off to our timers. There is also, in this particular device, another PLL. This one is being used to be able to provide a clock to the I2S peripheral, so that if we're using it to receive or transmit audio, we can use that as a clock source independent of the clocks going to the rest of the system. This one also has the ability to take a clock from an external source as well, separate to everything else if we need it to. So if we're slaving it to a device that's sending out digital audio and we're using the I2S in this chip to receive it, we might slave its clock to the device that's sending the audio in order to make sure everything stays nice and synchronized. Now, you can go through and actually use this to help calculate the particular clocks as well. So, for example, if we jump over to our pinout and configuration, and we will go to System Core, RCC, and we're just going to turn on our high-speed external clock. And we'll select bypass clock source for that one because we know that's coming from another chip rather than being a crystal. And if we jump back into our clock configuration, we can see that that is actually showing as being turned on now, which means that we can now select it as a source for the PLL. Now, say we want to be able to hit our maximum clock speeds for this device, which, as it shows here, is 100 megahertz. We can go, okay, what's 100 divided by 8? We're going to get 12.5. We can use our divider here to actually divide that clock by 2, which is going to turn it into a 4 megahertz clock. And 100 divided by 4 is of course going to be 25. So let's see if we can multiply this by, can't do 25, we can do 50. And then we could go divide by 2, which is going to give us 100 megahertz clock here, which is what we're looking for. We do, however, have a bit of an error over here. So if we hover over that, it's telling us that it doesn't like that because it wants our M output to be a frequency in between 0.95 and 2.1 megahertz, which means that in order to achieve that, we're going to have to go divide by 4. And then in order to get our 100 megahertz clock, we can double the figure that we're putting into our multiplier. So if we go multiply by 100, we can see that we've now got no errors showing up here, and we've got our 100 megahertz clock. You can go through and pop a value in here and get it to auto configure. I tend to find the auto configuration can take a little while though, and sometimes I like to challenge myself to be able to sit there and derive the clock manually. You can also do it with a pen and paper as well if you like. So we can see we're now reaching the maximum speeds that are capable for our H clock and for our peripheral bus 1 and peripheral bus 2 clocks, and see the outputs of the various clocks going to the different parts of the system. So that can actually be really useful to help determine that. And then I'd normally jot down the particular values that I've come up with on a bit of paper or take a screenshot so that when I actually sit to write the code to set the clocks up, then I know which values I'm going to need to be able to do that. One of the other things that we'll notice in here is there is also some MCOs or master clock outputs here, which allow us to send a clock from inside the chip outside the chip so that we can use that to be able to drive something else. So say if we were hooking up another STM32 to it and that needed a clock source, rather than adding a crystal, we could use one of the master clock outs, similar to what it's doing with the clock source that it's using that's coming from the chip doing ST-Link. The other thing we could potentially use that for is, say, if we were hooking it up to an FPGA to do something with a combination of the STM32 and the FPGA, we could actually use one of the MCOs as a clock source for the FPGA as well. So we're going to have a bit of a look at how to use those in this video as well, but just so that we know that they're there and there's something that we can actually use for the moment. So we're going to close this. We're not going to bother saving that. And we'll tell it we want the C++ perspective. I'm going to close our RCC files. And if you're using the QuartzArc code that is up on our GitHub, then all of the clock setup is done in the boot.cpp file. So in the core folder in the project, there'll be a boot HPP and boot CPP. The particular method that gets called to do all of that setup is the system initialize method, which is one of the first things that I call from main. And that will then go over to this particular method, which goes through and gets a bunch of things set up, including the clocks. So there's typically 2 or 3 stages that you go through to actually get the clocks set up for a device. If you're using the HAL like I do to actually set the clocks up, you're going to have one section which goes through and actually sets up the oscillators and typically the primary PLL. And then we'll have a section where we go through and actually set up the CPU and bus clocks, some of our clock dividers and things like that there. And then we don't have it in this case, but there may be a third section where we actually go through and set up peripheral clocks and select clock sources for specific peripherals that we're looking at using. On this particular chip, though, as we saw, the only peripheral that has the option to select a specific clock is the I2S. We're also going through and enabling the clocks for all of our GPIO ports as well. So in our oscillator configuration, essentially, we're going to go through and tell it what oscillators we're actually using. So we can tell it here that what we're actually configuring here is going to be our high-speed external, and tell it that what type of clock is connected to our high-speed external input. In this case, as we saw in the clock configurator, we're using bypass here due to the fact that we're pulling the clock source from the other chip. Otherwise, we might select crystal here if we were getting a clock source specifically from a crystal oscillator. We're also telling it we want the PLL turned on and that the source for the PLL is going to be the high-speed external oscillator. We'll go through and configure our PLL values. Now, as we saw before, we're actually using an M value of 4 and an N value of 100. Actually, no, may have been 2 and 5, but either way, these values do work. These guys do give us our 100 megahertz system clock. So we're taking our 8 megahertz, dividing it by 2, which gives us 4 megahertz, multiplying it by 50, which gives us 100, maybe, off the top of my head. I may not have that correct. Either way, before I get myself too distracted, these are the settings we're using, and these ones do actually work. So I may have some of these values messed up from the actual diagram. And we can double check that as well using a method that we're going to have a look at in the video. But this particular setup's giving us our 100 megahertz system clock, and then we're going through and actually doing our configuration there. In the second section, we go through and actually configure our CPU and bus clocks. We tell it which clocks we actually want to modify. In this case, we want to do our H clock, sys clock, peripheral clock 1 and peripheral clock 2. We're telling it that the system clock source is going to come from the PLL, that our divider for our AHB clock is going to be divided by 1 so that it's running at the same speed as our system clock. If we wanted the AHB to run at half the speed of our system clock, we could go div 2. There is various options. If we right click on this and go open declaration, we'll see there's a variety of options there. We've also got our peripheral bus 1 and peripheral bus 2 clock dividers. In this case, our peripheral bus 1 needs to run at half the speed of, or its maximum is 50 megahertz. So because we're running with a 100 megahertz system clock, we need that to run at half the speed, which is why we're going divided by 2 here. And then our peripheral bus 2 can run at the full 100 megahertz. So we're just going divide by 1 for that one. And then just telling it to configure that. And it's also getting us to provide our flash latency, which we're setting to 4 cycles there, which we might have a look at that when we do our video on the flash memory, which is coming up as well. So that's kind of a simple look at how we go about setting that up for this particular device. We will notice some similarities and differences with some other members of the family. If we go for our F030 device that we also have code up for on the GitHub, we can see that it's still fairly similar. We've got our high-speed internal and low-speed internal options here. We don't have a low-speed external option to be able to run the real-time clock on this particular device. We can select our high-speed external. The other thing to note here is that our low-speed internal is 40 kilohertz here rather than 32, which we had on the F411. We do have our high-speed external, which we are getting from outside the chip. In this case, again, we can select between a couple of different options to go to the PLL. We'll notice there's less options for the PLL in this case. We don't have dividers for it. We only have our multiplier value. And then, same as before, we can select between our HSI, HSE, or PLL clock for our system. And then we do have a simpler set of clocks for the rest of the system, simply because we only have one peripheral bus in this particular chip rather than the two that we have in most of the others. In this case, though, we can see that our USART1 does have the option to select between different clock sources. So it can either take its clock source from peripheral bus 1, from our high-speed internal, or from our system clock. So it does have a little bit more flexibility there. And there's also another internal clock source on this chip that we didn't have on the other one as well, which is a 14 megahertz internal clock that is used to drive the analog to digital converters, separate to the rest of the clocks in the system. We also have the ability to select between different clock sources for our I2C peripheral as well, as we can see up here. So a couple of different options compared to the F411. As far as actually configuring the clocks for this guy, it's still a fairly similar process though, is going through and actually configuring our oscillators. There is some different options here as far as providing calibration values and stuff for our internal oscillators, but still fairly similar. And then, of course, going through and configuring our CPU and bus clocks. The next one we'll take a look at is our F1 chip. So this is from a blue pill, which again, this code's up on GitHub. Again, fairly similar. Low speed internal, high speed internal oscillators, as well as the option to have a low speed external or high speed external. The PLL and system clock selection is all fairly similar. And fairly similar as far as clocks being set up for peripheral bus 1 and 2 and some of the other clocks for the system. This one has a single output for a clock, so that does give us the option to output a clock on this device if we want to. So again, fairly similar, but a couple of slight differences. Then we've got the F411 that we looked at. So that we can see another one in the F4 family, we've got the F429, which this one is on the F429 discovery board that I don't think we've actually had too much of a look at in any of the videos, but we will be doing some stuff with that coming up at some stage. And again, fairly similar thing. So LSI and HSI, as well as our LSE and HSE. This is pretty similar to what we saw with the F411, with the exception that we do have the ability to select different clock sources for our serial audio interface peripherals. It does have the option to be able to take an external clock for our I2S, much like the F411. And this one also has a third PLL, which is the Psi PLL, which goes to the serial audio interface, and is also used to provide a clock to our LCD TFT or LTDC peripheral as well, if we're using that. And again, same two options for master clock out as well. Next one we'll take a quick look at is our, not that one, the F769i, which we've been using with a discovery board in our Discovering STM32 series. So this one, again, fairly similar, same sort of clock sources. This one actually has 4 separate PLLs. So we've got 3 here. We've also got an additional one hiding down here, which is being used to provide a clock source for our DSI peripheral. In the Discovering STM32 series, we're using this one to be able to provide the DSI clock for transferring data between the STM32 chip and the LCD screen. And this one does give us a lot more options as to the particular clock sources that we're using for specific peripherals. So definitely a lot more configurability here. And depending on sort of how you go to set things up, you may need to be aware of making sure that certain clocks are set at a particular value in order for things to work correctly. So for example, with a project that I'm doing with the F429 at the moment, the main requirement in the clock setup for that is that the USB peripheral is getting a 48 megahertz clock, because we need to use that peripheral. That's the clock that it needs, which means that everything else as far as setting up CPU and bus clocks, stuff like that, kind of revolves around making sure that we're getting 48 megahertz to the USB, and then we can kind of configure everything else to fit within the parameters we need there, but still give us the sort of levels of performance that we're looking for. This one also does have a couple of master clock outputs, but aside from that and the additional PLLs and clock configurability of different peripherals, still fairly similar to what we've looked at with the other devices. The most complex one we're going to have a quick look at is our H743, which does have a little bit more complexity in the main clock section going to the different buses, simply because we actually have an AXI bus in this one, which connects the CPU to a bunch of the really high speed stuff, as well as multiple AHB buses, or advanced high performance buses, and also 4 peripheral buses rather than the 2 that we normally get in the other devices. So is a little bit more complexity involved in this one, but configuring it is still the same process, making sure that we're getting the particular settings that we need so that the frequencies we're getting to the different parts of the system are what we want them to be. One of the differences here is that the CPU is actually running at a different frequency to our highest performing buses in the system. So our CPU can run it up to 480 megahertz, whereas the primary clocks like the AXI bus is maximum of 240 megahertz, and then we'll notice all of our peripheral buses top out at 120 megahertz. Still very similar as far as PLLs and things like that as well, though. If we scroll down, same sort of thing, very similar to the F7 in terms of the level of flexibility with selecting clock sources going to various peripherals. Still got our clock sources that or master clock outputs that we can use. And this one also has an additional clock in it as well, which is a 48 megahertz clock, which we can use to do things like driving the USB peripherals and things like that at that specific frequency, rather than having to necessarily produce those clocks using the PLL's clock sources for that. So just some more options and flexibility there, but still pretty similar. If we jump back to our F411, one of the things that I do find really useful is being able to retrieve the speeds of some of the different parts of the system in software. And there is some methods in the RCC drivers in the HAL that we can actually use to make that happen. So we're going to have a bit of a look at those, which allows us to also see what frequencies we're actually running at. So we will create a variable to hold our frequency value that we retrieve, and we're also going to create a string just because we'll print these various clock speeds out to our serial so that we can see those as well. So let's just cheat a little bit, and we'll go with the here's one I prepared earlier option. So for this particular device, there is 4 different clock frequencies that the HAL can actually provide us. One of them is for the system clock frequency, as well as for our H clock frequency and for our peripheral bus 1 and peripheral bus 2 frequencies. Now, basically just calling that method, which returns the value in hertz of the particular frequency for each of these 4 methods, dividing it by 1 million so that we're converting it into megahertz, and then we're just going to be printing that out so that we can actually have a look at what those frequencies are. Now this can be handy for, say, if you're going to set up a timer and you want the timer to provide a specific period regardless of what, or a specific period regardless of what its associated clock frequency is. You can actually use these methods to return the frequency and use that to be able to calculate what prescaler you're going to need for the timer in order to reach the particular requirements you've got there. So let's have a look at what this looks like. So we'll just build that. We'll also open up our serial terminal here so that we can get some feedback from that and get that actually printing out. We're going to pop that code over onto our device and let's see what we get out of this. So it should be all running flat out with the way the clocks are configured in the code at the moment. And we can see that that is actually the case. So our system clock is running at its maximum 100 megahertz. Our H clock is also at its maximum. Our peripheral bus 1 clock has a maximum of 50 megahertz. So that's being divided down to 50 from our system clock frequency. And then we can see the peripheral clock frequency as well. So those methods can be quite useful for being able to determine what sort of speeds the device is actually running at. And those ones can be found in the HAL RCC H file for your particular device. So if we go down to find where these methods are at, in our exported functions, we can see we've got those guys there that we're using. Now, one of the other things that I wanted to have a bit of a look at in this video as well is as far as getting or making use of the master clock outputs. And I mentioned earlier the various reasons why you may do that. You might also find other uses for it that I haven't mentioned as well. But in this case, we're going to see how to actually configure it. And we'll have a bit of a look at what's coming out of those clock outputs on the oscilloscope as well, just so we can see what that kind of looks like. So using the clock outputs is really quite simple. It's basically just a matter of setting up the particular GPIO pins and then enabling the clock output, telling it what clock source that clock output is going to be using. So easiest way to find out which pins the master clock outputs are on is if we jump into our datasheet. So this is the datasheet for the F411. We'll go into our table of contents, pin out and pin description, and we want our alternate function mapping. And we'll see it in the left-hand column, the system alternate functions. Master clock output 1 is on pin A8, and master clock output 2 is on pin C9 in this case. So we do already have those connected up in this case to the oscilloscope so that we can have a bit of a look at those, but just so that it makes it a little bit easier for you to find those specific pins if you need to. That's the easiest way to be able to do that. So let's get our first one set up. We'll use both of them because we're actually going to do a comparison between our high-speed internal clock and high-speed external clock, just so that we can see what those are actually looking like. So that is pin 8. The mode we want for that one is going to be GPIO mode AF push pull, so alternate function push pull. we don't want to use a pull up or pull down on that one, so that'll be no pull. Our speed, we might just go GPIO speed frequency very high so that it's up all of the way, and set our alternate function, which will be GPIO 0, AF 0, MCO. And that again, you can help figure that out based on the table. If we jump over to here, we can see that those particular items come under AF0. And you can also find the alternate function mappings in the GPIO EX HAL file as well. You'll find all of the various ones for your specific device. So that's that one. Let's initialize that pin. That will be GPIO A, I believe it was A8 and C9. Yeah, C9 and A8, wonderful. So GPIO init on that one. And then we're going to go HAL RCC MCO config RCC MCO1 to say that we want to configure that clock output first. We're going to go RCC MCO1 source, and I think we can go with high speed internal for that one, maybe. I'll have a look at that. And we can also set a divider for this as well, if we choose to. We're just going to go with divider by 1 at the moment. Let's just double check our... So in here, in our rcc.h file, we'll find the particular sources we can select for MCO1. MCO2 has slightly different sources that can be selected, and those ones in this case will actually be found in the rcc_ex file. And we can see the options that we have as far as the divider for the or prescaler for those clock outputs as well. So we'll jump back into here. So that's configuring that one. Let's go with MCO2. The pin for that one, I believe that was C9 that we were looking at. So we'll go GPIO pin 9, HAL GPIO init. I'm not going to do all of the other settings as well because those settings are going to stay the same as what we've got for the first pin. And GPIO init, like so, and then we can go HAL RCC MCO config, RCC MCO2, RCC MCO2 source, and can't remember exactly which sources that one has off the top of my head. So if we jump into drivers, our HAL drivers, header files, and we want RCC EX. Just do a search for MCO2 source, and there we go. So we might grab the HSE for our second clock output, which works because we want to compare the HSI with the HSE. And we'll divide that by 1 as well. So that's going to give us our high-speed internal clock coming out of our MCO1 pin and our high-speed external clock coming out of our MCO2 pin. So let's just compile that, make sure that we've done all of that correctly. And let's get that dumped onto our device. Let's jump over to our oscilloscope, zoom out a tiny bit there. So I've also got the oscilloscope just measuring the frequencies of the two different clocks. That was from a previous run. Let's just adjust our settings here. Make both of these about the same. And we can see it's currently measuring our top clock, which is our high-speed internal, at just over 16 megahertz. And it's measuring our high-speed external at pretty much bang on 8 megahertz. If we do a single shot of that, we can see pretty much exact on 8 megahertz for our external clock. Whereas our internal clock, that's supposed to be 16 megahertz, is slightly off what we would have if we had an exact 16 megahertz clock. So like I said, the internal clocks are going to be slightly out. So even though it's supposed to be 16 megahertz, it may give you a little bit higher or a little bit lower, depending on the particular device. They will all be a tiny bit different. Now, just so we can compare them a bit better, let's divide our high-speed internal clock by 2, so that it should be then giving us a clock of 8 megahertz. So to do that, we're just changing our value here to MCO div 2, so that it's dividing it by 2. We'll pop that onto our device, jump back over to our oscilloscope, chuck it back into auto mode. Code's just copying across now. And we can see same thing again. We'll take a single shot, and this clock is slightly high, whereas this one is bang on 8 megahertz. Now we can select other sources and sort of see, for example, we could send our system clock out to one of the master clock outputs and have a look at that as well. This scope does only go up to 100 megahertz though, so if we're sending a 100 megahertz system clock out, it's going to have a bit of trouble trying to be able to measure that correctly, because it's sort of on the borderline of what this scope is capable of. But that kind of gives you a bit of an idea of how to use the master clock outs anyway, as well as sort of the accuracy difference in between the LSI, or the internal and external clocks. So this code I will pop up onto GitHub. This was just following on from the servo video we did, so I've just modified the code from there, so that'll be up on our F411 Quartz Arc repository. If you do have any questions about any of this, feel free to leave a comment in the description, or feel free to jump onto our subreddit, leave a question there if you've got any questions. Or feel free to send me an email. That works too. I do keep an eye on all of those. I did, as mentioned, code will be going up on the GitHub for this one. I will put a link to that in the description as well. So feel free to check that out. The next videos in this series, there's a whole bunch of them that I've got a massive list of videos I want to do for this series. Some of the things that we do have coming up though, we'll be looking at things like, even though we looked at reset and clock control system in here, we were basically focusing just on clocks. We will have a video where we look at resets specifically. We're also going to be doing a video where we look at things like power management, sleep states, standby states, that sort of stuff as well. One of the other things I will mention in here as well that I forgot is that it is also possible to reconfigure clocks while the chip is running, which is effectively what we're doing in the boot code anyway. The chip's already running at that point. You do need to be aware that it is communicating with the reset and clock control typically via peripheral bus 1, I believe it is, in most of the chips. So you want to make sure that you're not putting peripheral bus 1 or any of the clocks that allow communication between the CPU and that subsystem to be messed up, because otherwise you may lose the ability to be able to configure the RCC. The other thing to be aware of is, say in the case with what we've done here where we're outputting the clock frequencies via serial, if we were to dynamically go and change the clocks after setting up the UART peripheral to make that happen, we could potentially or likely end up in a situation where the UART is no longer running at the 57,600 baud rate that we had selected. So you may need to go and reconfigure particular peripherals so that they're still operating at the particular rate that you want. Same with things like timers. If you change the clocks that they're getting their clock source from, then the particular rate that that timer is running at is going to change as well. So you need to be aware of that. As well as if you've got SPI or I2C peripherals, you may find less issues with those because the peripheral, if it's acting in master mode, will be supplying the clock source. However, when that clock changes, as long as that clock speed is still within the range of what the device is connected to the SPI or I2C can operate at, then they should be fine. If you have an SPI device and you change the clocks and all of a sudden that the SPI bus is running at a rate higher than the peripherals connected to it can handle, you may run into a situation where it's not able to communicate with them effectively. So we will be looking at dynamic clocking and being able to increase and decrease the speeds of various parts of the system when we start looking at our Quartz Arc operating system video or video series. But it's a little bit beyond the scope of this video. I just want to make you aware you can do it, but there's certain things that you might want to be aware of if you're going to be dynamically changing clocks after everything's been set up. Aside from that, I want to say a huge thank you to all of the people that have recently subscribed, all of the people that have been watching the videos. It's really awesome to see people have been enjoying them. I think we've had just over 1,700 views in the last 28 days when I checked it before, and 229 subscribers, I think it was, which is really, really cool. So a big thank you to all of the people that have been liking the videos and leaving awesome comments, even just watching the videos. That's really cool. And a massive thank you to our two patrons, Craig and Luther. I think it's really awesome that they're helping to support the channel. That does help make it more possible for me to be able to continue to pump out videos more regularly and explore more interesting topics and things like that as well. So if you do want to help support the channel, feel free to check out our Patreon. Depending on which tiers you're looking at, there is various benefits that you get for that. So that's pretty much all I've got for this video. Just a bit of a look at STM32 clocks. I hope you're having a wonderful day or night, morning or evening, whatever it is in your part of the world as you're watching this. And thanks for watching.